Okay, welcome back. A few quick logistics. So you have a midterm in this room on Thursday. Hey. So just to be clear, so someone asked last time, is it open notes? And I said, yes, absolutely, it's open notes. We don't mean open internet. That would be hard to make an exam. So I mean, and I know the notes are mostly online in HTML. If you want the whole book, you're gonna have to, I don't know, you have to print it or something. I can't have the whole internet here. So anything paper is totally fine. You won't need a calculator or anything like that. Okay. There's a review session tonight at 7. Did you guys get a room? And it's posted on the web, or do you want me to say it? It's on the web. It's not for me to know. 4-270. Okay. The review materials, the practice midterms were posted, and we'll post the solutions now, pretty much, right after class. Right. Open notes, but not open internet. Okay. So we posted a problem set today, but that's just, it's not a real problem set. Don't worry, you guys, this is the one where we basically ask you one question, and it's, what are you going to do for your final project? So, think about the exam until Thursday, and then start thinking about what you want to do for the final project when you got some ideas and everything there. And feel free to ping me or the staff with questions, or if project ideas this week. And even when you give me you submit your homework, we will give you some feedback on that and try to get you a project of the right scale and everything. Okay. So I know we've covered a lot of material. I want to make sure people realize that the goal is not for you to understand every nuance of every algorithm we've touched, because that would be impossible. The goal is to understand how the algorithms can be applied, some of the basic things that we've hit over and over again, and to understand how the algorithms fit together. So hopefully the practice midterms that we've posted should give you a pretty good sense of the type of questions. That's the best way I have to give you a sense of what these things are going to look like. And the homeworks, of course, are the other good example. So today, instead of throwing a bunch of new material at you, the goal is to talk. It'll be a little fun, I hope. We're going to do running robots today, and it's going to rehearse. It's going to sort of practice the materials you've already seen, and tell you all about something a little new. Okay, so today we get to talk about running. And mostly robots, but maybe not all robots. Okay, so most people would think that running would be much harder for a robot than walking. It's kind of interesting that historically the running robots worked well before the walking robots did, right? So it's not to say that running is easier, but somehow experimentally it was easier to demonstrate. So the hopping robots I showed you on day 1, which we'll talk a bit about the control behind those hopping robots in the lecture today, happened in the early 80s and were extremely dynamic at a time where the walking robots were still shockingly slow and the like. And there might be a couple reasons for that. I mean, I think one of the reasons is that running is really somehow fundamentally about your center of mass dynamics, and all of the details of sort of your leg kinematics and the way your foot interacts with the ground and everything are somehow minimized, I think, when you're just trying to move quickly through the world. Sometimes moving fast is easier than moving slow. It's easier to stabilize a fast motion in cases. And I think in particular, it turned out to be that you could get away with pretty simple robots in the sense that they had relatively small number of actuators, small number of links, and could capture a lot of the dynamics of running. They looked like hopping robots first, looked like pogo sticks and the like. Whereas with walking, you sort of couldn't get around having an articulated leg, which meant waiting for motors that you could package like this and batteries that you could carry. It just somehow turned out to be experimentally harder to realize walking robots. Okay, but there's some beautiful work in running, and there continues to be beautiful work in running. And one of the things we're just starting to see sort of in the field now is robots that are mechanically sophisticated enough to walk that are also capable of running. That's only fairly recent that that's come together. For a long time, you either had a hopping kind of robot that was relatively simple and could propel itself around, or you had a big kinematically complicated walking robot, and only in the last handful of years have you seen both. So before we really dive in, I guess I have to tell you what the definition of running is, right? So what's the definition of running? What do you think?
Intermittent.
Yeah, sure.
Intermittent contact with the ground as you move forward.
Right. So
at some point you're not touching the ground.
Have the existence of an aerial phase. You're going to say the same thing. The first and simplest definition. I don't know why my pen makes me look like a crazy today, but I'm not going to change it. Unless that becomes really distracting, I think it would take a recalibration to change that, but my writing is not quite that bad. Okay, definition 1 is the existence of an aerial phase. Some point in a quasi-periodic motion, let's say, you have no points of contact with the ground. That's absolutely a good, reasonable definition of running. It turns out people needed more sophisticated, or a little bit better definitions of that, because there's all these counterexamples that don't quite look like walking, look like they should be called running, but don't necessarily have an aerial phase. Anybody old enough to remember Groucho Marx? Yeah? So there's actually scientific papers that talk about Groucho running, because he has a way of running, which I have too many cables attached to me to demonstrate, where he moves along in sort of a clear running gait, but his feet never leave the ground. Okay? So there's another definition of running. Does anybody know the other definition of running? The biomechanics definition of running? Say definition 2. It talks about the exchange of kinetic and potential energy. Okay? So specifically, walking, the motion, the transitions between kinetic and potential energy for walking sort of looks like vaulting. So some of the earliest models of walking really thought about your center of mass sort of vaulting over your stance leg. So your center of mass goes up and over during the stance phase. Okay? So your potential energy peaks during mid-stance. And running, a very useful definition of running, is when the opposite happens. When your stance leg actually compresses during the stance phase, and you have an opposite exchange of kinetic and potential energy. So in this cartoon, I mean for the dot to represent your center of mass, and maybe in a generalized way, this could represent some center of pressure on the ground, which we mentioned quickly when we talked about ground reaction forces before. Some single point to represent the net force on the ground. Okay. And so in running, your potential energy actually drops through mid-stance. Okay, and there's all these really great exceptions. Groucho Marx is one of that's sort of become famous in the biomechanics literature because someone wrote a paper calling it Groucho running and it somehow stuck. But there's actually a lot of great examples. So first of all, the question about the aerial phase was initially, it turned out back in the day, people didn't actually know if animals were getting aerial phases. And there's this famous story of Leland Stanford, of Stanford University, who basically had a bet going with one of his friends that his racing horses actually obtained an aerial phase during the races. And nobody knew, because cameras back then, if you took a picture of a running horse, were just a blur, right? And so Edward Muybridge was a radical photographer of the time, and he was paid to basically invent a type of photography that allowed him to take pictures like this. Basically, he invented the shutter for a camera, and was able to take some of the first pictures that definitively showed an aerial phase, even in a racehorse. Yeah, and he's actually credited with as being one of the fathers of motion photography now, right? But there's all these other quirky cases too. So that was in the late 1800s. 1878 was this first sort of famous picture. Even just about 10 years ago, people were still debating whether an elephant runs. What do you think? Do you think an elephant runs? What do you think? Yes? Yeah? Turns out the answer is pretty complicated. And the way you figure it out is you start motion capturing horses, okay? And actually the audio on these videos are hilarious. You're like, yeah, trying to egg on this elephant as he runs around. And the answer turns out to be that most elephants don't obtain an aerial phase. Every once in a while, you'll see an elephant that can actually get an aerial phase, but most of them don't. So then you have to go to definition 2 and ask, what does the center of mass look like? What does the exchange of kinetic and potential energy looks like? What do you think? Running or not running?
So I was going to say that I guess the exchange of the center of mass would be like, it's trying to exchange the load front and back. It looks like it's running, the back feet are running, the front feet are running, but in between it's kind of holding it.
Did you get all that out of this one video?
Yeah.
That's amazing. So you're actually really, really close. But it turns out if you look at the exchange of kinetic and potential energy, the best answer that these guys could give, they said basically it breaks the mold. But they said if we have to give an answer, we would say the back legs are running and the front legs are walking. Right? And unlike most animals, actually all of the legs are breaking at every step. They're just doing so much work to hold up their mass that they're totally bizarre. Their front legs are walking and their back legs are running. That was the official Nature paper result. Okay, so there's no simple answer for, there's always these corner cases. But there are simple models, okay? So not surprisingly, we're going to be able to understand a lot of things about running by looking at a few simple models. So today we're going to do simple models of running. And we'll get back to some of the robots that have been built which match the simple models better than you see in walking robots. This is like the Halloween font or something. Maybe it doesn't look as bad to you up there, but in high resolution it looks ridiculous. Okay. So let me just take a quick aside and make sure that there's sort of this nice story that goes along with the simple models of running that I can't help but tell you guys. So quick aside, let's talk about the value of these simple models. Let's say virtue number 1, right? The one we've been capitalizing on is that the simple models are analytically, computationally, pictorially simple to get our head around, right? So analytically sometimes, even graphically tractable. And that's a big deal for us. And that's really the reason that I've been talking about them, in the class so much. I think really that infers deeper understanding of the fundamentals. Okay, but some people, let's say virtue number 2, some people are actually able to use those simple models to make a more general statement. Okay, so sometimes you can actually, they can yield general results or conclusions. Okay, so insights. So here's an example that I didn't quite get to before, but it's worth mentioning now. So remember the simple model of walking, where we had a pin joint in the back foot, let's say. We had the foot about to come into contact, and our model for the energetics of walking was dominated by the notion that the center of mass, your momentum right before contact, had to look like this. It had to be a right angle here. Your after contact, it had a right angle here, and there was this story about losing energy like that, right? So one of the things that people have extracted from this sort of very simple model is a nice energetic story about walking. So they said, for instance, this is Andy Ruina's story, one of his many stories. So what if you could put sort of push off with your toe right before impact? Okay, and in the simple models, let's call it an impulsive push off. So it happens instantaneously, and that's just equivalent to what's the role of pushing off with your back foot right before you contact. It turns out the timing of that can have big implications on the energetics of walking. In particular, if you manage to toe off just before this foot comes in contact with the ground, then an impulse here could change instantaneously. Does the green show up okay? Yeah. Can change instantaneously. This could be from an impulse. Your total momentum, so that at the moment of impact you lose much less, right? Do you have any colors left? Not really. But right, if I can use an impulse, if I can use my push off it right before I'm coming down to the ground, I've got all this energy that's about to be lost into the ground. If I can push off right before, then I can reduce the ground speed of my foot, suffer much less of an inelastic collision, lose much less energy, and it's a very simple sort of picture that you can see right here. And it can sort of dramatically reduce your losses due to collision. Right? So Andy has this great quip. This is Andy Ruina at Cornell, who's one of the prominent names in passive dynamic walking and walking robots. He had a nice paper with his colleagues saying that you can be 4 times more efficient to toe off before heel strike. As opposed to if you wait till your heel strikes and then push off, that's a lot worse. And by dimensionless arguments, he's actually able to give some sort of quantification to it that in dimensionless terms, you can actually have a 4 times factor of efficiency. Okay, so that's just a simple, nice story that tells you something about, that's going to generalize to more complicated robots, right? That I can reduce the ground speed of my foot that's about to come to collision with a toe off. And that can be a big role that it has to play, right? And that's a story that comes out of the simple models but generalizes much beyond that. And I would argue that it would have been, if we had been looking at Asimov models the whole time, or Atlas models, or some complicated models, we would never have had such a clear story about that. Okay? But there's another virtue, the one that comes up today, that comes into play, which is that some of these simple models have actually, sort of using that sort of idea, have actually started to give back and been used by biology to start making predictions and summarizing data in biology. So there's a movement that Bob Full at Berkeley likes to, has been one of the leaders of, that they call comparative biology. Where they're using simple models to find principles that hold across a wide variety of animals. Okay, so the picture I showed, which is one of the topics we're going to focus on today, of running as sort of this motion like this, it turns out a nice model for that is to have is if you had a spring in your leg that compresses with a constant stiffness. It's called the spring-loaded inverted pendulum model. Slip model. Okay. Constant stiffness spring. In the leg. And looking at it turns out that simple model not only is going to be interesting for our robots, but it turns out that simple model has been very predictive in biology. That if you look at the center of mass and center of pressure dynamics of animals when they run, and again, that's the center of pressure, not the foot. So you've got some animal, I don't know, a boxy horse, right? So just drew the horse's leg backwards, but you know what I mean? Right? So I've got a center of mass here. I've got a center of pressure here. But what would make it better? I mean, so it turns out if you model the horse as a spring mass runner, I'm an engineer, not an artist. Then the gross center of mass dynamics of the I almost said the robot, of the horse actually match surprisingly well with the dynamics of a spring-loaded inverted pendulum, okay, with a constant stiffness over the course of a stance phase. But what's really surprising is that not only does that model work for a horse, but it also works for a cockroach, right, which is sort of 5 orders of magnitude smaller in terms of just mass, right? And in fact, they could even predict sort of the stiffness, the relative stiffness compared to the mass, and even that matches sort of surprisingly well. I grabbed a figure from their paper here. Look at this. This is the relative individual leg stiffness. If I model these guys as a constant stiffness spring, and they normalize for mass, right? Then the relative stiffness sort of looks like a surprisingly good model, and happens to be a relatively constant number across a surprisingly large range of animal models. Okay, so it turns out to be predictive in that sense. And notice that what's really interesting about this is that the variety of gaits in here is extreme, right? So a cockroach has 6 legs. The kangaroo's hopping mostly on 2, although they use their tail, right? The human's got 2 legs. That's their robot, Rex, right? But rabbits, quails, horses are in here somewhere. This one maybe. I mean, different numbers of legs, different gaits, but they're all sort of running with this sort of characteristic spring. So maybe that means they found something primal about biology by using these simple models. Okay, I think it's hard to generalize to anything in biology. If I've learned one thing talking to the biologists is that biology is messy and complicated. But that seems like maybe a defining principle. And there's some question of whether that's a principle that was talking about the central part of the motor control system, or if it's because they've got springy tendons in your legs. There's been a lot of work relating the stiffness from these models to the tendon stiffnesses in your legs. So it might be a physical reason, it might be a cognitive reason, although cockroaches don't have that much cognitive ability. But there's lots of interesting questions there, but it seems at least predictive across a large range of animals. And sort of the last virtue is one that I want to say carefully, and so I'll just put it in the corner because I want to say it carefully, right? Because, but some people use this as a template for complex robots. And I'd say the jury's still out whether that's the right thing to do, but you know, one argument is if horses run with a center of mass model that looks like this, and I've built a robot that has 62 motors in it, maybe what I should do is I should try to take my big complicated system and make it act using sort of control feedback to design to make it act like a spring-loaded inverted pendulum. And that may be the right thing to do, given that mechanical machine that's not a biological thing, it might not be the right thing to do. But that's an active area of research, is sort of the idea of embedding simple models as the controllers for a more complex model. Okay. So let's dive in and start looking at the dynamics of the slip model using our Poincare analysis and everything. Okay, it's a nice example. It follows what we did last time, but it's a little bit richer. So, so I think it's a great example for today. So the slip model, spring-loaded inverted pendulum. Okay, so drawing it a little bit more carefully here. Got a big mass, a leg with a spring. Wow, I think the reason you guys didn't like my course is because the tablet's not working right. I think if it hadn't been for that, it would have been, you wouldn't have laughed, I'm sure. So I'll worry about the angle of the leg relative to the ground, the mass of the body, the length of the leg, of course, is now a new variable. And it'll have a nominal leg length, I'll call it L0. There's also now a stiffness parameter, a stiffness of the spring we'll call K. And of course, we've got gravity pointing down. Okay, and we'll also talk about the XY position of the body. Okay, so the state of this guy in general, well, the configuration of it is described by the X position of the center mass, the Y position of the center mass, and the angle of the leg. Okay. Now, to make this a nice tractable model, we're gonna make some assumptions, right? We're gonna say that the leg and the toe are completely massless. Okay. So you should immediately say, how can that possibly make sense? I mean, maybe that makes sense when you're on the ground. You can just put a point here, and then you still have the mass dynamics like this. But when I'm in the air, I'm running, how can that possibly make sense? Okay, that implies that we're going to have to assume in the air we're not modeling the swing leg dynamics. We're just going to assume that you have a controller that can instantaneously place the leg wherever you want it to be for the touchdown angle. So we're going to command touchdown angle. Directly and not model the stance, the swing leg. Okay? But the reason to make that assumption is that it also now implies a perfectly elastic collision. We used inelastic collisions last time. We're going to take the other extreme this time. Okay, so we have no energy loss to the toe because I'm going to assume the spring is perfectly efficient. There's no impact here. Anything, as the contact is made, any energy is stored in the spring and then restored as you bounce back. Okay, so that means actually there are no energy losses in this system. So if you're so inclined, you might already have a problem with this. Presumably, we're going to ask about the stability of this thing. Is it a stable hopper? What are our chances of getting stability if the energy is always conserved? Not so good, right? So dissipation is, oh, sorry.
So if you're assuming that there could be an area phase here, potentially the next state variable, because L is variable, right?
Oh, I'm sorry. L is in this too. Thank you very much. Forgot to write L in here. Also in stance, we need L. Yeah, I just forgot to write it. Good catch. Right, so if you have a system that has no energy losses or gains, then you're not going to have a stable system in the full sense. But what we're going to have is something, a partial statement of stability, that sort of on the, what we're going to work towards is, given the constraint that energy is conserved, the rest of the states, it will not be stable in perturbation and energy, but in every other direction it could be stable. Okay, but that, you know, that actually implies can't be stable in the full sense. But what even the dynamicists have been really excited about is that these systems, which are piecewise Hamiltonian, right? So the Hamiltonian systems are the energy-preserving systems. They can exhibit stability-like properties. Some of these hybrid systems that a system that conserves energy in every hybrid mode, but switches between hybrid modes, can exhibit some stability properties beyond what you'd expect from a normal Hamiltonian system. But it will never restore a perturbation in energy, so it won't ever be really stable. Okay, so this is still going to be a hybrid model, right? So there's a collision that has no losses, an elastic collision when the foot hits the ground. And then we'll say the robot leaves the ground back into the aerial phase whenever the leg reaches its rest length. So we'll just say the spring extends, and when it runs out of run, then the robot will leave the ground. Okay, so this gives you a slightly quirky but effective model of a hopping robot, which you won't be surprised to know you could easily put in the software and simulate. So I could probably have tuned the parameters better, but here you go. Here's a running robot that falls into a stable hopping cycle, okay? Stable up to the perturbations in energy, yeah? Okay, so let's try to understand that model using the return map machinery. And so it turns out it's stable even if you just leave the touchdown angle as a constant. Okay, so won't write stability, but long-term dynamics. Okay, so just the controller's doing nothing. It's just saying the same thing every single time. Touchdown at this angle. And you saw in the simulation, it hopped up and immediately just, the leg just went forward as soon as it was in the air, which it could have penetrated the ground. There's all these problems with not analyzing the swing dynamics, but if you make that assumption, then you've got a simple model to work with. Okay? So let's see if we can do our Poincare map analysis on this. Okay, so the rimless wheel, we chose the surface of section to be at the instant when the foot hit the ground. Actually, we put it right after the collision. Where do we want to put it for this one? You have lots of choices, really. You could put it at the impact. You could put it a bunch of different places. It turns out that one of them is going to be special in the sense that we're going to be able to use less variables to describe it. You could do this in some other state too, but it's easy to describe the system when you look at it at the apex. Okay, so we'll do an apex to apex map. So at the highest point in its aerial phase. Okay, so at the apex, we have x, y, theta, x dot, y dot, theta dot. L is a constant in the air. We don't model L in the air, right? So I'll just write it L and L dot. Okay, but in general, that looks like it's going to be a hard thing to plot from all those variables to all the next variables. But it turns out things get simpler quick, okay? So first of all, we already said that the angle we've basically taken out of the equation said that we're not modeling the swing dynamics, so those are irrelevant to the dynamics, right? And these are constant. The leg length is a constant in the air, and so L dot is 0. So we don't really need to include that in our map. If I tell you I'm at the apex, I already know what L is, so I can infer that from the other variables. What else? So X doesn't really, I don't really care where I am in the world right now. I don't expect to be stable in that variable anyway, so I can ignore that one. Y dot, the apex is defined by the place where y dot equals 0. So I can get rid of that one too. And suddenly I'm just left with y and x dot. If I know y and x dot, I can infer what the other state variables must be. So I can write my dynamics as a function of y and x dot and get to the next one. Turns out I can do even one better, which is all I need. I can infer one of those from the other because I know that the energy of the system is conserved. So if I know the total energy, I can the energy is a function of y and x dot. So if you give me y, I can deduce x dot from y also. Right? If I know the system has some amount of energy in it, you tell me where I am in y dot is 0, I can figure out exactly what x dot has to be. Okay? So the result is I can actually write a Poincare map at the apex, which is just a map from the y height at the nth crossing to the y hat at the next nth crossing. Right, so there was a good question on the discussion forums about what dimension do we write down p in? And when you're doing it numerically, you often choose the full n dimensions, and you can take eigenvalues and the like, and I guess the homework's done, so and then you get a 0 eigenvalue out, right? When you're doing analysis, you do your darndest to get it down to the minimal description of it. Of course, you're living on an n-1 dimensional manifold at least, and it turns out this slip model lives on even a one-dimensional manifold. So you might as well write it down with one variable. Okay? Does that make sense? If I know the y position at the apex, then I know everything about the state of the hopper. And I can simulate forward by figuring out from y all the state variables and running my simulation forward. Okay? Now, the simulation has a couple different modes in it. In fact, if you look at the model, there's a flight mode and a stance mode in the hybrid system. And there's a transition that goes from flight to stance. Okay, there's a transition at the apex where I'm going to figure out my return map. And then there's this transition from stance to air, which has these takeoff conditions. Okay, so there's two modes, and there's transitions back and forth between them. It happens that because we were taking the analysis at the top, I put the flight in two separate modes. So there's a flight 1 and a flight 2. The flight 2 is up to the apex, and then there's a transition to the next one, just so we can write the Poincare map there at the apex. Okay. All right. So in the flight phase, I mean, the dynamics are easy of this thing, right? In the flight phase, the dynamics are just a point mass moving through the air. Yeah?
You get away with not having L be variable? Like, going to the flight phase?
The flight phase, L is irrelevant, but in the stance phase, L will just give you the dynamics.
In the flight phase, the spring will keep compressive stretching.
So there's a question of if it's a good model, and I agree that any real system, if there's any, will have mass at the toe, and therefore the spring will have non-negligible dynamics in the air. But we've assumed that for the massless toe, the leg is not doing anything in the air. We're just assuming that away.
That's my model.
I would say it's a questionable model at best, but it seems to describe a lot of data. That's the justification. Yeah.
And a related question, right? So you said that the top-down angle could be made constant, right? That sounds fine.
Well,
but you also said that you don't have to model the angle at all. Like,
that's totally bogus, right? I mean, it irritates me to no end every time I write this model down that we're ignoring the swing dynamics, right? But if you're going to get a one-dimensional return map out of it, the reward for being blasé about the swing dynamics is that I can draw a picture for you, right? That's really the only justification I can give you, is that it seems to match data, and it's going to let me draw pictures and understand things.
But for example, to generate that simulation in MATLAB that you showed, you have to model the angle.
No, I just didn't have that state variable in the air. I set the angle, and I'll write down the dynamics for you. But I can always infer in the air, I just don't simulate. I just say the leg like this constant. I can check when that angle hits the ground, right? I can write down that function easily. And then during the stance dynamics, I simulate the dynamics of the leg length. Okay, but then when I just lock it for the so L dot is 0 during the air, and that's fine. That's a reasonable model. To draw it, I had to just write down L dot equals 0, but I actually didn't need that for my model. Okay, so in the flight phase, it's just a ballistic dynamics, right? So I don't have to write that down. It's y double dot equals negative g. It's a point mass, let's say. Never mind. It's always the negative g. That's silly. Right, so that's easy to simulate. Easy to solve analytically. It's a linear system. X dot is a constant, right? X double dot is 0. There's no drag. I mean, if I'm ignoring the swing leg dynamics, then you can be sure I'm not putting aerodynamic drag in here. Okay. And I can simulate this thing forward just fine, right? In the flight phase, the dynamics are given and are linear. So what's more, I can integrate analytically from the apex to the touchdown condition, which is when y of t equals L0 cos theta touchdown. Abbreviate touchdown. So I can find the time where that happens by just solving the linear equations and back out the state at the touchdown. Okay? There's no change in velocity at the touchdown, but there is a change of coordinates because in the stance phase, I'm going to use a different set of variables. I'm going to switch to my state being the length of the leg, but I'll, r or theta. I want to just think of it as a polar coordinate, so I'll call it r for a second. Theta dot. And I'm going to switch to a dynamics like this. So the reset map that I build here is really just resetting to these different coordinates. Okay. And the dynamics here are easy to derive from the Lagrangian too. I just have a potential energy in the spring in addition to the potential energy due to gravity. I can write down my Lagrangian mechanics and write those equations down too. They're on the paper that I've scanned and they'll be in the notes. But the point is that there's some nonlinear terms in there. There's sines and cosines in there. So actually figuring out integrating the dynamics across the stance phase to the moment where the takeoff happens, I can't do analytically. So there's nonlinear dynamics. Okay. Unless I'm willing to make a small angle approximation, right? If I assume that I come down at a small angle and sines approximately 1 and sines approximately theta and cosines approximately 1, then I can get a linear approximation by making a small angle assumption. Okay, that's something that Hartmut Geyer recommended. Hartmut's on the faculty at Carnegie Mellon now. His student work, he studied the slip model. Thank you. Hartmut Geyer. Okay. And there's even one more annoying thing you have to do because the linearization is wrong. It doesn't conserve energy. So you have to, even though you linearize, then you can get a closed form map because it's a linear system. But then you have to do a little correction to make sure the energy is conserved to make it a reasonable map. Okay. What I want you to get out of this is that we can do a Poincare map analysis on more complicated systems. The modes might involve changes of coordinates. They might involve nonlinear dynamics in some phases, linear dynamics in other phases. Our analysis sometimes involves approximations of those. Okay, but the general picture I gave you before of simulating up to a guard, doing a jump equation, simulating beyond, even if you have a limit cycle having to go through multiple transitions, right? These things, all the tools still work. Okay, and you can do it for slip, and with some approximations, you can get that. This is the other model where you can get a closed form solution from one surface to another surface. Okay? When you do that, you get sort of a pretty picture out. Okay? Let me try to draw it carefully here. This is y at the nth apex versus y at the n+1 apex. Now remember, for the Poincare maps, the line of slope 1, it's a discrete map, so the line of slope 1 is an important line. And this map is sort of, there's some y where it doesn't make sense to go below it because there's no aerial phase, right? At some point I have to have a minimum y for my model to make sense. If I start below the leg length, then it doesn't make sense, okay? But it's well defined above that, and I get a picture that looks like this. Okay, so we can ask, the fixed points we know are where these things cross. And you remember that the way you move around on these iterated maps is if I were to start with some initial y, okay, and I go to the next, I simulate for one cycle, and I'm going to get a larger y now. That's going to take me to here. Project back to the map, right? Oops, did I screw up? No, that's right. And then that's going to take me to here, and this thing's going to oscillate and come in to be stable. Similarly, if I were to start up here, I go here, right? Do this sort of staircase dynamics. So this one becomes my stable fixed point. On this map, okay? But, and this one is an unstable fixed point. If I start here, now actually, given a constant energy, people might ask, you should think like, what would it mean to go off to infinity sort of on that? It doesn't really make sense. The model stops making sense up here. Why is that? What's the other sort of limit of this model? The small angle assumption is no good, possibly, but there's another reason. Sorry? Yeah. Not what I'm looking for, but. So in order to make this plot, I had to choose a particular theta touchdown, and I had to choose a particular energy in the system. And if I start going up with y larger and larger, then at some point I don't have meaningful, all my energies in potential I've exceeded my energy in potential. So there's no energy left for x dot. And somehow it doesn't make sense to go back up past my total energy in the system. The robot stops. Or even before that, the robot will have so little horizontal velocity that it'll come in and it won't make it over the hump. It'll just fall down, which the model does do in simulation. Okay. All right. So this is with a certain set of parameters that the energy was in a normalized units and everything like that. But this is a characteristic. So this complicated hopping system still has this stable fixed point here, which of course is a function of the parameters you pick. But there is a stable hopping solution that you can actually draw and understand with all these Poincare tools, given a few assumptions. Okay. Now, just to say it one more time, I put stable in quotes, it won't reject perturbations in energy. Right? So in the full coordinates, it would look like having multiple eigenvalues of 0. And a perturbation along the energy would have an eigenvalue of 1, I guess. But it's never going to reject perturbations in energy. Okay, so the initial motivation of that model was to understand the vertical dynamics of the center of mass. Okay, but the biologists really loved this. You could predict, and it would work for crabs running sideways, and it worked for cockroaches, and all these crazy things. So they started looking for it in other places, right? And the lab that studied the cockroaches, Bob Full's lab, found that even the horizontal dynamics, the lateral dynamics of the cockroach could roughly be described with these models. Okay? But you might ask, how the heck do you measure the dynamics of a lateral perturbation on a cockroach? Okay, so Bob Full's lab is awesome. They have, so one of the reasons, they had to make a ground, basically a force plate to measure the ground reaction forces for a cockroach. That sounds like a hard instrumentation problem. The way they solved it is they found a way to put Jell-O down with a diffraction grating on the top and the bottom, so that when the cockroach pushed the Jell-O, it would bend the light, and they had a force sensor based on making the cockroaches run on Jell-O. And apparently orange Jell-O was good because they ate that a little bit slower, but they still ate it. So it's sort of annoying that they would eat their force sensor. Okay, but that's not the best of their experiments. My favorite by far was when they were actually trying to figure out how do you perturb the cockroach, right? So how do you put a lateral perturbation to the cockroach? These guys are moving pretty fast. So you'd like the perturbation to be a subset of the time of the stance dynamics for it to be meaningful. You'd like it to be an impulse, right? So they were trying to tie strings and all these things. It was really, really hard, okay? The thing they came up with was just, in the end, was just awesome. So let me show you the video first, okay? So that's a cockroach. And on top of the cockroach, you might wonder what that is. You get a little hint there. So don't be distracted by the ball here. That was actually an accident that it bounced back. This is a cannon so the nice thing about cockroaches is they have exoskeletons and you can bolt things to them, okay? So let me play that again. So this is a cockroach with a cannon strapped to his back. And as he's running, the cannon explodes right about here. It happens in this particular video, the ball came back and you got a second perturbation, but that wasn't really the point. And the great thing was that they were able to measure the kinematics of this guy, and although it took him a few steps to correct his orientation, his horizontal velocity was corrected within a single stride. And it matched, what they were looking for was this lateral leg spring dynamics, so a spring mass model in the horizontal. Okay? So they argued with that not only that it was that the spring mass model generalized to horizontal, but actually that it had to be a physical spring in the leg because it was too fast for neural conduction in the cockroach. Now the great thing is, I know Devin, who did this experiment in Bob Full's lab. He gave me the video, and he said sort of on the side, I was asking him about what it was like to do that experiment. He said, first of all, it was crazy getting permission to do it, right? That was a lot of work, right? So even though you can do anything you want to an invertebrate, apparently, but still having gunpowder in the lab is not good. He just, on the side, he mentioned one day, he said, it's surprising how little gunpowder you need, right? And I thought to myself later, like, there must have been intermediate experiments, right? Where it's just like, there's, where'd he go, So I love that kind of science. Okay. All right, so it turns out that the spring-loaded inverted pendulum model has had uses here. It's also been generalized now. People used to think of, like I said, walking as vaulting over a stiff leg. Nowadays, people think about the role of compliance even in walking. That's been cleared that's important also in walking. Your center mass still goes up, but your leg does bend a little bit in walking, and that's an important part of the dynamics. And there's been nice work that Hartmut went on to talk about these models here, which could produce both walking and running. by modeling now the swing leg dynamics when appropriate, okay? Having two legs, basically two spring mass models. And this model with different initial energies can give you both walking and running, okay? And what's more, he argued that the ground reaction forces produced by the model were somewhat reasonable compared to biology. Okay, so let's do a little bit more. So this was all given a constant command, right? So let's think about how would you do control on the slip model, okay? All right, so what we've given ourselves now is a map from apex to apex, which was parameterized by my control parameter, my touchdown angle, right? So you can ask, how do I design a controller? If I wanted to design a controller to potentially move the fixed point to make it more stable, I could design the controller to live right on the return map. I could wait for the system to get to, in fact, it doesn't really make sense to move the leg between that. So when I get to the top, I'll look at my state, I'll look at Y, and I'll choose a new touchdown angle for the next state, right? Theta touchdown at the nth step. Okay? So how could you do that? How would you design that controller? Well, there's a lot of nice methods to do it. So hopefully the first thing that comes to your mind is I could do LQR, right? I could linearize the map P. I'd end up with a discrete time map. Maybe I'm in my bar coordinates here. Right? And then I could do LQR. And that'll work well. And now you remember that you've done the discrete time LQR also on the homework. It's a little different than the continuous time, but totally doable. That works well. But there's actually a nicer trick. There's a nicer way to do it for the case where I know P and it's a sort of simple function that I can reason about numerically, if not, if I have the linearization assumptions, I have it analytically. If not, I could get it numerically easily. And it's something that's sort of unique to discrete time maps. You don't typically think about doing it in continuous time. But certainly for walking, it's a powerful idea. And that's the idea of deadbeat control. Right, so in continuous time, it takes time to get wherever you're trying to go. If my goal is to get to the origin, I have no choice but to go sort of slowly to the origin. And taking an exponential progression towards the origin is a perfectly good thing to do. In discrete time systems, I jump. So there's no requirement that I take an exponential path to the orbit. I could actually go boom right to the orbit in a single step. That's something that you can do in a discrete time system that's not as natural in a continuous time system. So So I can literally, when I find myself in some Y, I could start interrogating P. I could evaluate it every possible theta touchdown for my current Y and find the theta touchdown so that my next one is going to be 0, or is my Y desired. That's the idea of a deadbeat controller. Get there in one step. And you can certainly do that for the slip model, and that's the sort of recommended control for slip, is compute that on every step, put your angle at exactly where you need to be, so on the next step you're at your desired hopping height. The cool thing is that the function that emerges, my control function, if you look at the thing you solve for, it's a smooth function such that if I didn't know, it's hard for me to say this quickly, but let me see, I'll try. Imagine that I'm hopping along and I don't know the height of the ground, okay? But I'd like to maintain some constant height. It just so happens that for the slip model, if I had to go through and I put myself at a theta touchdown at a certain angle and sweep it through at a particular rate, then that function exists such that whenever I happen to hit the ground, I'll be at the deadbeat controller for that height, and I'll hop back up. Okay? So if I just put my leg blindly through some schedule, whenever if the ground happened to be high, I'll hit it early, but that happened to be I want to have a slight angle when I hit it early. If the ground was low, then I actually want to have a steep angle so I can put it more back up into vertical. So I just run through a schedule like this, and independent of ground height, I can always be at the deadbeat controller. Okay, that was another result by Hartmut. And that's the video that I put in the wrong order here. This is what that looks like. His model of slip here just hops along and will always get back to the nominal height, independent of what the ground's doing, just by following this schedule. And they even put it on this little robot here. And it wasn't perfect. It went up a little bit, but that's a pretty cool idea that you could get. You guys were asking about open loop stability before, right? This is a nice example of open loop stability that are actually robust to the terrain just by having a deadbeat controller on the schedule. Very cool idea. Okay, so in the last few minutes, I want to sort of tell you how the slip model actually helps us understand the way Mark Rabert built his hopping controllers, which came first, actually. Mark Rabert built his hopping controllers well before people were talking about slip. In fact, you could say that the slip models sort of came from people trying to understand how the heck Mark Rabert's controllers worked, okay? So you remember the hopping videos I showed you before. The first robot that Mark built was this hopping robot here that had weights out on the edges, okay, to make the inertia of the body large. It had two actuators. It has a piston in the leg and then a torque actuator, so that's a pneumatic actuator in the length of the leg so that the pneumatics could act as like a spring, and then you could inject energy if you like. And then it had a hydraulic torque actuator at the hip. Okay? And you actually, on day one, simulated that controller, right? Had this simple model hopping around in MATLAB, right? And that had my approximation of his controller. I wanted to make it time invariant, but other than that, it's almost exactly his controller. And it turns out his controller, I'm not supposed to show that yet, his controller is surprisingly simple, right? So all this talk I've been doing about, which I very much believe in, about optimization and everything like that, he didn't do any of that, right? He uses physical intuition, and in general has been a proponent of intuitive control, and came out with something that worked very nicely to stabilize the simple hopping machines, okay? So I'll just sketch the ideas behind that. So he wrote his algorithm in 3 parts, okay? The first one was a controller that just controlled hopping height. The second controller controlled only body attitude, pitch of the body. And the third one controlled forward speed of the robot. Okay. The hopping height controller was sort of painfully simple. So my predisposition, if I were to build a hopping height controller for a robot like this, is I'd start modeling the basic impact dynamics of the ground, some of the pneumatics in the leg, come up with an approximate model. We can do all these things, and that recipe will work for more complicated machines. But for this one, Mark in his lab said, you know what? If I hold the pneumatic pressure constant, every time the robot goes down, it's going to lose a little energy in the cylinder and start hopping slower. But if every time the foot hits the ground, I just put a constant amount of energy in, just every time the foot hits the ground, then it's going to go back up, and it'll find some stable hopping height for any constant energy in. And if I turn that number up, it hops higher. And if I turn that number down, it hops lower. So that's good enough, So that was brilliant. I mean, so basically, he had a simple dial that would control the hopping height of the robot. And if the foot's moving around, yeah, that changes the map a little bit, but it's still monotonically. The hopping height will still be monotonically related to where I turn the dial. So that's my hopping height controller. It's a dial like this. If it looks like the robot's too low, I'll turn it up, right? So the key observation was that the hopping apex height, let's say, related to input command, which was a pressure. And that was it. So, and then so Dan Kodacek, for instance, went back and analyzed simple models of that hopping robot and showed for reasonable models of the leg spring and reasonable inputs and everything like this. And it was, in fact, a return map that we could understand to have a stable fixed point, right? But Mark knew that, and he just turned the dial, and that was his brilliance. Okay, same thing for body attitude. So how do you control the pitch of your robot? Well, that's tough, right? So like when you're in the air, you can't control your total angular momentum, but you can sort of move things relative to each other. That's hard, right? What I'm going to do is I'm going to put the inertia of the body out on the edges of the rod here, so that when I'm moving around in the air, my leg is pretty light relative to my body. So basically, I'll move my leg around to do what it needs to do in the air, and the body's not going to move very much, right? And if it's moving a lot, I'll put a little more mass up there, right? Simple. So that allows me to decompose the controller. And then at the moment when the foot's on the ground, then now a torque at the hip, you have sort of you have the mass of the earth on the other end, right? So, so you can now impart a torque on your body during the stance phase. And he just did a position control of the body during the stance phase and left it alone in the air, right? And that was enough to do body attitude control. Although when I've played with the controller, and I think when people afterwards have played with the controller, this is the most sensitive part. This is the hardest part to tune in, right? And of course, when I'm doing position control of the body during stance, that's also affecting the leg angle, but we'll just ignore that. Yeah, that's and then the forward speed is maybe the most interesting. And you'll guess the theme here, but Mark basically observed that at steady state, if I put myself down at a certain touchdown angle, and this, remember, predated the slip model, for a certain touchdown angle, there was a magic touchdown angle where I'd come off symmetric, okay? Where I'd come off at the same angle here as I did here, okay? There was a Okay, so he did some work to figure out what that touchdown angle looked like with a simple model. Again, before slip, but the slip can help you understand this too. And then he observed that if I put my foot a little bit in front of that, what happens? I slow down, right? Because I come out, I come in and I come out less, more vertical. So I'm trading some of my energy into the air. And if I want to go faster, I put my foot down a little bit before that magic point, and I'll come out faster. So my speed controller was a position control on the ground for foot placement, which mapped to a touchdown angle command at the hip, so you can move your swing leg like this. Okay? Very simple, very robust controller that worked on the real hardware, way more dynamic at the time than anything else out there. Right? So, and let me show you some of the things he did with it. So from this, I mean, you can see my implementation of the controller there, but so he went on to build two-legged things that could hop over and do flips I showed you before. He went on to build quadrupeds. Now you can see by the resolution of the video, this was a long time ago, yeah? Right? This was the quadrupeds. He's got a great paper that's called Running on Four Legs as Though They Were One, okay? Where it's told the story of taking that simple monopod hopping idea and making the virtual leg spring, which was kind of like this picture I've been showing you with the slip model, and using that to program the quadruped and the biped. And this thing could do a lot of the quadruped gaits dynamically. It's very simple. It's not doing foot placement, right? So if there was stepping stones it had to run over, that's tough. There was actually Jessica Hodgins who did some work on trying to do foot placement in that framework for simple things. But this is just a very simple, make the robot the right way and you can do simple control idea. And really, that has been the story that has continued to work. This is Big Dog. So Mark Rabert left academia, started a company, Boston Dynamics. They did simulation for 10 years. And then he came back, and I was in the leg lab the day that he came back and he said, is anybody using that treadmill over there? I'm going to start building robots again. And a few years later here, there's Big Dog walking around. And the story that they tell about the way the controller works here, I think there's massive amounts of very talented engineering in here. But basically, the idea is the same. The body is heavy. The legs are light. The torque, the power in the actuators is sufficient that if you kick it, it can always put its leg out where it needs to get this basic speed controller in 3D working. And that was enough to get these guys walking around and sort of, I'd say for the first time, making legged robots look like a real thing that would really work in the world. It's just awesome. And then from there, they went off and they've just, I mean, the story is really, they've got slightly different simple models now. They've got really good state estimation, really good control of their actuators. They've engineered the heck out of it, but the control story is still surprisingly similar to the story that they tell about the hoppers. Okay, so I think this is where we're at right now. And I'll just end by saying that actually, so what we're working on in our group is sort of what I hope to be, and other people are working on too, is sort of the next. You guys aren't going to listen to me if I put that on. So let's say you do want to do that with stepping stones or with more complicated contact. If you wanted to build an American Ninja Warrior robot or something like this, right? then the tools we've been talking about will still work, right? So our version of trying to make Atlas work, we did trajectory optimization. And we asked for a periodic solution to Atlas running, and did a lot of work to try to write that down in a formulation that was simple enough that it could be run quickly, and use a simple, important way, some tricks to write down the problem, so that it had less local minima and the like. But now we can have Atlas running, and our same code didn't require assumptions about the robot or whatever. Can do the same thing for little dogs. So for better, for worse, the tools that we're using with trajectory optimization and then stabilization with the quadratic programming stabilization that Scott told you about can solve these harder problems, okay? But they're not nearly as simple, nor robust yet, really, as the controllers Raber showed. They do generalize, so we can make Atlas do all kinds of crazy things, and I hope you'll see the real robot doing that soon. Good. So we'll see you here on Thursday, and perhaps tonight at the review session.